Hello everyone, welcome to my YouTube channel. My name is Tushar Shenoy. I am a student at NMAM Institute of Technology. My passion lies in the fascinating world of electronics. Today, I am excited to present to you an amazing project in digital system design. In this video, I'll be explaining and demonstrating a 4-bit binary code converter. So let's dive right in. Let's quickly understand what a binary code converter does. In digital systems, binary is the language computers use to represent and process information. Binary code converters are essential components that allow us to convert data from one binary format to another. So what is a 4-bit binary code converter? A 4-bit binary code converter is a circuit that can convert a 4-bit binary code representation from one form to another. The digital data is represented, stored, and transmitted as group of bits. This group of bits is also called as binary code. Code converters are used to convert the information into the desired code. The four types of codes which are included in this project are binary, XS3, BCD, and gray code. For this project, I designed a 4-bit binary code converter which can convert binary numbers between different formats. The converter can handle 4 bits of data and perform conversions between binary, BCD, and gray code representations. Now let us understand the objective and types of binary codes in this project. The objective of the project is to design and implement a circuit which will perform 4 different binary code conversions depending on the initial inputs. The types of binary codes are gray code. Gray code is a non-weighted code where each successive code differs in only one bit position known as a unit distance code. The circuit will be able to convert binary numbers into gray code and vice versa. This conversion is useful in various applications including rotary encoders, error detection, and analog to digital converters. The second type of code is XS3 code. XS3 code is another non-weighted code that is obtained by adding 3 to the corresponding BCD value. The circuit will have the capability to convert binary numbers into XS3 code and vice versa. This code is commonly used in digital calculators as it simplifies arithmetic operation and reduces errors. The third type of code is BCD. BCD stands for Binary Coded Decimal. BCD is a weighted code where every decimal digit is expressed by a separate group of 4 bits. BCD is widely used in applications such as digital displays, numeric keypads, and real-time clocks. By implementing this circuit, users will have a versatile tool that can handle various binary code conversions efficiently. The circuit will provide accurate results and aid in simplifying data manipulation in digital systems. Now let us go through the circuit design. Let us see the components used. The first component is IC74153. It is a dual 4-input multiplexer. The second component is IC74139. It is a dual 2 to 4-line decoder. The third component is IC7432. It is a quad OR gate. The fourth component is IC7486. It is a quad XOR gate. The fifth component is IC7408. It is a quad 2-input AND gate. The sixth component is IC7404. It is a hex inverter, or simply we call it as NOT gate. The seventh component is LM7805 IC. It is a 5-volt voltage regulator. The eighth component is common cathode 7-segment display. The ninth component is a diode. The 10th component is 6-pin button switch. The 11th component is 9-volt battery. So these are the corresponding quantities required of each component. Now let us look into the code conversion table. This table represents the demultiplexer select lines and the corresponding code conversion. For 00 combination of the select lines, the converter performs binary code to gray code conversion. For 01 combination of the select lines, the converter performs BCD to XS3 code conversion. For 10 combination of the select lines, the converter performs gray code to binary code conversion. And for 11 combination of the select lines, the converter performs XS3 code to BCD code conversion. So now let us look into the block diagram of our circuit. Here we have a demux and all these are the mux which will perform code conversions. The Output of demux is connected to the enable pin of mux. For a particular combination of the select lines, a particular code conversion gets selected and it performs the code conversion. For 0 combination of the select lines, this mux will be enabled and all these muxes will be in off state. So it will perform binary to gray code conversion, and these are the converted outputs. Now let us look into the circuit diagram. This is the demultiplexer circuit. Here S1 and S2 are the select lines, Y1, Y2, Y3, Y4 are the output of the demux, which are connected to the enable pins of the mux. This is the circuit of binary to gray code conversion, and this is the circuit of BCD to XS3 code conversion. Please note that A and B of all these circuits are shorted. Similarly, C and D of all these circuits are shorted and given as the inputs. These are the reduced outputs which are fed as input, which we obtain from the truth table of the code conversion. This is the circuit of gray code to binary conversion, and this is the circuit of XS3 to BCD conversion. Now let us understand the logic used to display zeros and ones on a 7-segment display. Let me take you to the Tinkercad. So this is the logic which I have used to display zeros and ones. We know that either to display 0 or to display 1, B and C of the 7-segment display should always glow. So I have shorted B and C and given it to the positive power supply, whereas the other 4 LEDs, that is A, F, E and D, is shorted and given to the output of the NOT gate. So when the input to the NOT gate is 0, the output will be 1 and it will display 0 on the 7-segment display. When the input to the NOT gate is 1, the output will be 0 and it will display 1 on the 7-segment display. So this was the logic used to display zeros and ones. Now let us look into the working. The 4-bit binary code converter circuit using demultiplexer and multiplexer works as follows. Initially, the demux is used to select a particular conversion out of 4 different conversions. The output of the demux is applied to the enable of the mux. The select lines of the demux determine the conversion which has to be performed. The inputs A, B, C, D is given once after selecting the conversion which is needed to be performed. The logic gates like OR, NOT and XOR are used to perform operations on inputs C and D, and the output of the logic gates is then applied to the input of the mux. The mux is used to map the reduced outputs of a particular code to output, and the conversion to gray code or XS3 code or binary is performed. The selection lines of the mux, that is A and B, determine the mapping of the binary code to the gray code or XS3 code. The output of the mux represents the converted code in the desired format. The converted output is displayed on the 7-segment display along with the LEDs. Now let us look into the project demonstration.
So this is the circuit of our project. These are the 6-pin button switches. These are the 7-segment displays. This is a demux. This is a NOT gate which is used to drive these 7-segment displays. These are the muxes which will perform code conversions. These 4 are the basic gates. If you look closely in the circuit, I have connected diodes at every output. As I have shorted the output and to prevent the inflow of current into the gates, I have used a diode. Now let me demonstrate my project. These two are the select lines. These are the inputs. So if I press this switch, it will be 1. If I again press it, it will be 0. So whenever I press a switch, it will be 1. And again if I press it, it will be 0. For 0-0 combination of the select lines, the circuit will perform binary to gray code conversion. So as the binary inputs are 0, 0, 0, 0, the output is also 0, 0, 0, 0. Now if I change the input to 0, 0, 1, 1, that is 0, 0, 1, 1, the output should be 0, 0, 1, 0. Now Again, if I change the input to 1011, that is 1 0 1 1, the output should be 1110. As you can see, the output and this output both are matching. Now, if I change the select lines to 0 1, now the circuit will perform BCD to XS3 conversion. So, as the inputs are 0 0 0 0, the output is 0 0 1 1. That is, for the input 0 0 0 0, the output is 0 0 1 1. Now, if I change the input to 0 1 1 1, that is 0 1 1 1, the output should be 1 0 1 0. And as you can see, the output is 1010 here. Now, if I change the input to 0 1 0 0, that is 0 1 0 0, the output becomes 0 1 1 1. So this circuit works fine for binary to gray code conversion and BCD to XS3 conversion. Now let us check the vice versa case. Now, if I change the select lines to 1 0, the circuit will perform gray code to binary code conversion. So, for 0 0 0 0 combination of the input, the output should be 0 0 0 0. As you can see, the outputs are matching. Now, if I change the input to 0 1 0 0, the output should be 0 1 1 1. As you can see, the outputs are matching. Again, if I change the input to 0 0 1 0, the output should be 0 0 1 1. So 0 0 1 0, the output is 0 0 1 1. Now, if I change this select lines to 1 1, the circuit will perform XS3 to BCD conversion. So, now the circuit should perform XS3 to BCD code conversion. So now, if I give 0 1 1 0 as the input, the output should be 0 0 1 1. So let me check. 0 1 1 as the input, the output is 0 0 1 1. Now, if I change the input to 0 1 1 1, the output should be 0 1 0 0. So the circuit works fine for all 4 code conversions. So this was the demonstration of this project.
Thank you everyone.